Hi everyone, in this video we are going to learn how you can implement WGAN in TensorFlow. So first of all, in WGAN the most important part is the loss function. So let's see how we can implement the Wasserstein loss function. But before moving towards the implementation process, let me clear here an important point. So from the implementation point of view, this Wasserstein loss function will try to increase the gap between the score of the generated image and the real image, and we will see how it is going to do it. So if you look to the original paper algorithm where they propose this WGAN architecture, in case of training the critic, this is the loss equation. So here, as you can see, under this for loop on the third line, or on the fifth line, we have this loss function. So this is basically the Wasserstein loss function, and what it is doing, firstly, this part represents the average critic score for the real image, and then we are subtracting average critic score for the generated image. So if I write this expression in bit more readable form, it will look something like this. The critic loss is the average critic score on the real image minus average critic score on the generated image. So this is going to be my critic loss. And then how the generator loss is going to look like, it will be the negative average critic score on the generated image. So on this line 10, you can see that it's the average critic score on the generated image with a negative sign. Now the magic is done by these negative signs. So let's understand how they are going to increase the gap between the real image and the generated image. First of all, in case of generator, why do we need this negative sign? So if the critic output a larger score for the generated image, this means this negative sign is going to convert that score into a smaller loss. So for example, if the critic output 50 for a generated image, so this negative sign is going to turn that 50 into negative 50, so our loss will become small. So this phenomena encourages the critic to output larger score for the fake images, because only then the loss is going to be small, and this is our ultimate objective. We want our loss to be small. And in case of training the critic, a larger score for the real image will result a large loss value, because as you can see in this critical function, we don't have any negative sign with the critic value for the real image. So we are going to keep the critic value of the real image positive. So this means if the number is high, the loss is going to be high. So our objective is going to keep this number smaller. So the critic will try its best to output a smaller value for the real image. This means that our model is going to output a smaller value for the real image, because only then our loss will be small, and big value for the generated image, and in that case only then our loss will be small. So that's why this Wasserstein loss function, when we will implement in the GAN context, will try to increase the gap between the scores of the generated image and the real image. So I hope you have understood this point. Now in order to get these negative signs, what I'll do, I'll multiply the generated or fake image score with -1, because if I multiply the score of the generated image with a -1, I'll get this negative sign. And similarly for the generator, I'll do the same. I'll multiply it with -1. And in case of real images, I'm going to multiply it with 1, so it is going to keep this number positive, and I'll use these -1 and +1 as my true labels. If you still have confusions, don't worry. In the next slide we will see how you can implement it, and that is going to clear your confusions. So the coding is going to look something like this. This is our Wasserstein loss function, which is going to take y true and y pred, and what we are going to do is to multiply this y true with y pred. So y pred are basically the critic score for the images. Either it could be generated images or real images. So we are going to multiply this y true with the critic score. So in case of generator, this y true is going to be negative, and in case of real images, this y true is going to be positive. And then we are going to find this reduced sum in order to get Wasserstein loss, and then we are going to return that Wasserstein loss. Below this function, first of all we need to find the batch size, and then for the real images my values will be positive ones, so tf dot ones, and then batch size. And for the fake images or generated images, I'm going to multiply with negative 1, so that's why I have put this negative sign and then tf dot ones. So this is how I'm going to calculate my real and fake labels. And then in order to get that y pred, I'm going to say pred underscore fake is equals to critic and give me the score for these fake images. So I'm going to pass my fake images to critic. Remember, critic and discriminator are same things, but in WGAN we call discriminator the critic. Okay, so I'm going to pass my fake images to the critic, and critic is going to output score for these fake images, which I'll call pred fake. And then I'm going to pass my real images to critic, and it is going to output score for the real images, which I'll call pred real. Then I'm going to calculate the Wasserstein loss for each of them. So with the fake prediction, I'm going to pass my fake label. So these are my generated images score. So in case of generated images, remember we are going to multiply it with negative 1. So our fake label is negative 1, and we are going to multiply it with negative 1. So this means larger the value, smaller the loss function. And then in case of real loss, we are going to pass our real labels, which are positive ones, and then the prediction or the critic score of real images. So smaller this value, smaller will be the loss. Our ultimate objective is going to output a smaller value for the real images and a bigger value for the fake images. And finally, in order to get the total loss, I'm going to sum them all. I hope now you are familiar with gradient penalty. We have discussed it in the previous video in detail. So if you haven't watched that video, make sure to watch it, because you have to understand the reason why we are doing this. Now let's see the critic training step. Before understanding this code, it's important to see the actual algorithm first. So this is the actual algorithm, and on the top we have some parameters, and one of the parameter is this n critic is equals to 5. So this basically means that we are going to train our critic 5 times in a single training cycle. So we are going to train our generator only one time, but critic 5 times in a single training cycle. So that's why you can see here we have this for loop which is iterating on this n critic. So we are going to train our critic 5 times, and then we are going to train our generator. So that's why we need a separate function for critic which is going to train the critic 5 times. So this is my critic training step, and in this critic training step, first of all we are calculating the batch size, then real labels, fake labels, so 1 and negative ones, and then we are sampling a random normal distribution which I'm going to pass to the generator in order to get fake images or generated images. Then we are going to use this tf gradient tab in order to calculate the gradients, and we are going to use this tf.gradient tab 2 times. On one gradient tab I'm going to record my gradients for calculating gradient penalty, and on other tab I'm going to record the gradients of model variables with respect to total loss. So that's why I need two gradient tabs. And here first of all I'm going to pass my fake images to the critic in order to get the fake critic score, and then real images to get the real critic score. And then I'm going to calculate my Wasserstein loss function. This is the gradient penalty step. We are going to calculate the epsilon, then interpolated images. I'm going to watch for the interpolated image, and then I'm going to calculate the gradient for the interpolated image. I'm going to pass this interpolated images gradients to the penalty gradient loss, which is going to give me the gradient penalty based on this interpolated images gradient. So this is going to like find the L2 distance, and then we'll subtract -1, we'll square it, and we'll multiply it with lambda, and then it will return the gradient penalty. So once I have fake loss, the real loss, and gradient penalty, all I need to do is to sum them all in order to get this total loss, and then I'm going to find the gradients of the critic variables with respect to this total loss. Using the optimizer, I'm going to optimize my variables and will return the fake loss, real loss, and gradient penalty, because we are going to need these three variables in order to train the generator. Now let's see the complete training step. So this is how the complete training step is going to look like. First of all, in order to evaluate the model image generation abilities, I'm going to sample a normal distribution which is going to act as a validation input for the model, and then I'm going to convert my non-iter dataset into a iterable dataset. This for loop is responsible for the number of epochs. Then I'm going to set critic.trainable to true because we need to train the critic, and then I'm going to iterate on the critic training cycle. So in the original paper, the critic training cycle were 5. So this is how the training of critic is going to look like. Take a batch of real images and then pass that batch to this critic training step, which is going to return us the fake loss, real loss, and gradient penalty, which we have learned in the previous slide. And I'm going to sum them all in order to get the critic loss. And then in case of training generator, I'm going to get the batch size, and now I'm going to trick my critic. So I'll say that my generated images are actually real images. So that's why I'm going to use this tf.1s instead of negative tf.1, which we did in the previous slide. And before training my generator, I'll say critic.trainable to false, and then I'll say WGAN-GP.train on batch. So this is exactly what we did with DC GANs or vanilla GAN. So I'm going to use this WGAN complete model in order to train just the generator by putting the critic dot trainable to false. So this is how we are going to do the training of WGANs. And in the next video, we are going to see the screencast of the coding, and I'll see you there. Bye bye.